We all have that one equation floating in the void of our middle school memories. Area equals pi r squared. You probably accept it as a hard fact of nature, but knowing a sequence of letters and numbers is a long way from actually understanding why it works. Finding the area of a standard shape like a rectangle is completely intuitive. You take straight lines and build a perpendicular grid. We can count perfectly stacked square units and easily measure the space inside. Try shoving rigid boxes into a curved boundary and you immediately hit friction. The square corners jut out over the rounded edges. You can't easily measure continuous sweeping curves using straight, rigid lines. But what if we didn't have to? What if there was a physical way to flatten the curve, forcing a round object to reveal the straight lines hiding inside of it? True mathematical literacy comes from learning how to physically translate a complex shape into a simple one, rather than just memorizing a static rule. Let's change how we look at a circle. Instead of a solid, flat plane, imagine it as a tightly wound spool of thin string. It snaps apart into thousands of delicate, concentric rings. Now, take a pair of geometric scissors. Start at the outermost edge and slice straight down to the exact center point. Because we severed the loops, the entire spool unravels. The rings detach at the cut line, peel open, and begin to fall straight down. The massive outer ring hits the ground first, forming a wide, flat base. As the progressively smaller inner rings fall, they neatly stack on top of each other. The unraveled circle naturally forms a solid, straight-edged isosceles triangle. We haven't added or removed any mass. We've taken an unsolvable continuous curve and physically rearranged it into a completely standard, measurable polygon. This technical diagram maps out our physical thought experiment. We have our original concentric circle, labeled A, and an angled projection line pulling its rings down to form what's labeled triangle 1. We need to define the vertical height of this new triangle. That measurement is exactly the length of our initial scissor cut from the edge to the center. It's simply the radius, represented by r. Next is the massive bottom edge stretching from F to G. That base is our unrolled outermost ring. The full length of a circle's outer edge is its circumference, which makes our long base exactly 2 pi r. We can make this even simpler. If you slide the horizontal layers sideways until they align perfectly on one side, you get this blue right-angled triangle on the right. Its overall area, base, and height stay exactly the same. Now we apply the universally known formula for the area of any triangle: 1/2 times the base times the height. Substitute our circle's physical dimensions into that formula. We get 1/2 times 2 pi r times r. Let the basic arithmetic run its course. The 1/2 and the 2 perfectly neutralize each other. Multiply the remaining r by r, and we are left with exactly pi r squared. The formula pi r squared represents the literal geometric footprint of a flattened circle. No material was added or removed to reach that answer. We solve the math purely through a change in visual perspective. This introduces the concept of accumulation. It's the realization that incredibly complex wholes are built by stacking infinitely thin, highly measurable parts. This process of breaking a curve into a stack of simple, straight lines is the same logic used to calculate volumes and slopes in calculus. It provides a way to solve the infinite through the finite. In this light, mathematics becomes a fluid language of physical transformations rather than a list of static equations. The complexity of a curve is often an illusion. Unrolling the shape reveals the simple, straight-edged layers waiting underneath.